We're now going to look at some of the material covered in this module of MATH201. We're dealing mainly with exponential functions. Exponential functions are something you should have learned about in your algebra classes, but they spend a fair amount of time reviewing exponential functions and actually doing lots of problems with an exponential functions, and then also, of course, including a calculus and a derivative aspect to it. But really, this is a lot of algebra. It's going to be also a lot of exponential functions, and also in order to solve these problems, we're going to have to use the natural log a lot. So a lot going on here. So let me try and take a few minutes and sort of summarize exponential functions. And then we will do some example problems that will hopefully help you as you're working through this section. For an exponential function, let me write the basic equation, and I'm going to do it in terms of time. My variable is going to be time. So I'm going to call it capital F sub t. So here's a function with respect to time. Now let me write this out, and then I will explain what it is. This is a basic, we could call this really natural exponential function, because look at this exponent here, the base is e, right? You all should know that e is that special constant. It's really a constant that occurs in nature. It happens naturally, and that's why it gets used so much. As a matter of fact, as we start working with these exponential functions, you'll end up seeing a lot of the problems are story problems because they sort of occur in nature. And there's a whole list of all the different kinds of problems that ended up using this natural exponential function. I mean, first there's like science. You'll see some science problems. You'll see some biology problems where you're looking at bacteria growing, or the amount of medicine in your body, how it's decreasing and how we're tracking it. There's a huge number of problems that deal with money and finance. And just so you know, if you recall, when you had to do some financial equations, there's one type of financial equation. When you invest money in a bank, one of the options for your investment, they say it's compounded continuously. Those are key words, because when they use those words, they're telling you the equation you're going to use is an exponential, natural exponential function. So sometimes in some problems, they will say it's a natural exponential function. But a lot of times with money problems, they'll just say the money is compounded continuously. Well, this is code for saying this is the kind of equation you're going to use to solve the problem. There's also problems, maybe I'll call these social science. Social science problems mean like looking at population trends. I mean, say they want to look at the population of a certain county over a 10 or 20 year time span, then they will use some kind of natural exponential function. Something else they use, maybe you've heard of this before, stuff like carbon dating, where they look at old rocks or pieces of wood, and they look at the amount of carbon that they can find in that rock. And by using a special exponential equation, they can go back and calculate how old they think that rock is. So we're going to see some story problems, and you have all these different kinds of problems, but all these kinds of problems are all going to be based off of this kind of a function. So let's take a few minutes, quickly review what all this stuff is, and then let's dive in and start looking at some problems. So this is your function. So say, for instance, just for fun, say we're looking at a population problem. They've studied the population of a certain city, and they're trying to look at the data and they're trying to come up with an equation for the population growth of a city per year. So for that kind of problem, maybe they'll call population T. So that's the population. T is time, and in this case, they're looking at it every year. So then you notice my equation is for P of T. This is like function notation. But here, it's always the same variable, but you got this little circle here. This is actually pronounced in the math world. We call this P naught. And honestly, I don't know where that little phrase naught comes from, but this would be called F naught. This is P naught. That little circle down here makes it the naught. But actually what this is, and I'll explain this a little more in a minute, we call this, wow, I can't write, the initial value. So for this problem, we're looking at population. So P of T is the population based upon, we're going to plug in a year here, and that's the population. P naught is the initial value of the population when we start our study. Normally when you study population, normally you would say okay, we're going to start looking at 2010, and we're going to study until 2025. So 2010 is almost like when the clock starts, when we start looking, we start watching. So what they do is the time will be 0 when you start the study. So if we look at it for 15 years, and if we're looking at what happens in 2025, T would be 15. In this case, P naught says, what is the population when you first start? In a sense, you could say P naught is the population when the time is 0. So with all these exponential functions and equations, this number here, it's a constant. It doesn't change. It's just a number, and we call it the initial value. So we've got our function, our initial value. E is just the base of our exponent. This is the natural exponential. And then we've got KT. Well, for our example, T, once again, is time in years. But then what is K? Sometimes they give K a different name, but oftentimes I like to call it the growth rate. The value of K is going to really determine how this function grows or how it decreases, whatever's going on. K is really important. K is, once again, it's a constant. It's just a number. Just like this P naught is a number. K is also a number. T is your variable. T is the thing that can change. So for instance, if we're having, I'm just going to make, this will be totally sort of meaningless, but just to give an example, I'm going to say, maybe it's some small town. So here's an equation for the population, and I'm going to say the K is 0.05. So here is a typical looking exponential function, and I'm going to call it a population growth. What does that mean? Well, let's do this here. We start 2010, 2025. I've already given you the initial value. So in 2010, the population is 5,000 people. Just to be very clear, I can write it over here. What if someone says, what's the population in 2015? What's it going to be? Well, for 2015, T is going to be 5, because that's 5 years past our starting point. So for 2015, I would plug in 5 for T into this equation. And then this would calculate what the population is. So you take your calculator, hopefully you know how to do this kind of math on your calculator. So I have 0.05 times 5. Now for me, I have this little in yellow, this e to the x. The way I access that is I hit this yellow button. When I do that, this number here is e to the 0.05 times 5. So this whole thing here is like 1.284. So I'm going to multiply that times 5,000. So maybe this is like the population of a small town. So it starts out at 5,000. After 5 years, it grows to 6,420 people. So we could say P of 5 is 6,420. So that's how these kinds of exponential functions work. Now let me just show you while we're here. This will save us time later on. They'll throw you some curveballs. Here's a common one. What if they say, during what year will the population equal 8,000 people? So we know we start with 5,000. We've seen after 5 years, it grows to 6,420. They're saying, how long does it take for the population to reach 8,000 people? So to make it clear, let me rewrite my population equation. So what they're really saying is, they're saying, let's set the population to 8,000 and then take this equation and then solve for T, the time, the number of years. See up here, when I said, what's the population for 2015, we set T equal to 5, which means we put T equal to 5. We did the calculation and the population was 6,420. Now we're doing the opposite. I'm going to stick in a number for capital P. I'm going to stick in 8,000. And now I want to solve for T, because this is basically going to tell me how many years it's going to take for the population to hit 8,000. Now this is a little tricky problem to solve, basically because T is up here in the exponent. So this is something we're going to do a lot in the examples that we do in a few minutes. So we might as well go over now the method to solve an equation when your variable is part of the exponent. First thing we're going to do is we want to get the exponent by itself. So I want to move this 5,000 to the other side. So I'm going to divide both sides by 5,000. And just to make it simple, let me go ahead and just put a number here. In the future, you can do all this on your calculator, but I'll just do it now while we're trying to explain it. It's 1.6. So 1.6 equals e to the 0.05 t. Now, to solve for t, you have to remember back to some of your rules about natural logs and exponents. Hopefully you remember, if I have a variable up here in the exponent of a natural exponential function, the way I can get at this is I need to take the natural log of this. Of course, I have to take the natural log of both sides. Because if you remember from logs, that special rule is when you take the natural log of e to an exponent, this whole thing ends up just being the exponent. So that's very handy, because now I have this equation where the natural log of 1.6, and this is just a number. In a minute, I'm going to let my calculator figure out what this number is. Natural log of 1.6 equals 0.05 t. So if I want to solve for t, I divide both sides by 0.05. So basically t is going to be the natural log of 1.6 divided by 0.05. That's a pretty simple calculation on my calculator. Matter of fact, my 1.6 is still here. So let me take the natural log. So here's my ln key. I hit natural log. Then I'm going to divide by 0.05. And the answer is 9.4 years. So basically, just a little bit after 9 years, that's when the population of this town will hit 8,000. So let's take a quick step back. What have we done? We have looked at the basic natural exponential function. We decided to do a more concrete example of looking at like population growth. And I've made up a little problem here for like a small town that starts out with 5,000 people. And we can determine, look at future years, what the size of the population could be. And we also said, hey, instead of looking at future years, how about we choose a population and figure out how long it's going to take for the city to grow that large. So this is an example of all the kinds of math problems we're going to do. And it's all based upon these exponential functions. Now let's take a step back and let's talk about these functions a little bit more. There's a few things you need to understand before we start working problems. And here's a key. So here's my basic exponential. Matter of fact, I apologize. Instead of saying natural exponential, I'm just going to say exponential. But of course, we're working with the natural exponential, but I get tired of saying natural exponential. So just to sort of save my breath, I'm going to maybe most of the time just say exponential functions. Here's our basic exponential function. Now this function, actually two things can happen. You might have a situation like we just talked about. Our example here was population growth. We called it growth because the population was growing. So many of the problems we're going to work with these exponential equations and it end up being called exponential growth problems. So whatever we're looking at is growing. Matter of fact, exponential growth means it grows really fast. It can grow fast, very quickly. But there are other problems that we're going to work at, and we're going to look at. And they're not exponential growth. It's not growing. It's actually called exponential decay, where actually the value is dropping over time. So really, there are two kinds of problems we can have based upon this exponential function. It can either be a case where whatever we're looking at is growing, it's getting larger, but other times that's actually getting smaller. Now, what's the key to knowing what kind of problem we have? The whole key is K, which we called our growth rate. What happens for exponential growth at K, whatever number is in front of this T here, if it's a positive number, if K is greater than 0, if K is positive, then this function will be exponential growth. It's going to grow. It's going to get bigger. However, there are other times when you look at this exponent and up here, the number in front of the T is a negative number. So if K in a sense is negative, then that's called exponential decay. As time goes on, the value of the function is actually decreasing. It's getting smaller. So we're going to work both kinds of problems. And it's very, very easy to tell. You just look at the number in front of the T up here in the exponent. If it's a positive number, we know it's growing. That's an exponential growth. If it's a negative number, it's a decay. It's getting smaller. As a matter of fact, just one quick thing. If you were actually to look, we were to try and graph out. Now here, I'm not going to graph time because, you can't have negative time. All the examples I'm talking about, most of the problems we're going to deal with time. So you start at time 0 and time is always positive. But just for fun, I'm going to graph over here just f of x. Instead of time, I'm going to use the variable x. So theoretically, x can be positive or negative. But anyways, here's what an exponential growth graph looks like. When x is negative, it starts really small. Then it starts to grow. And then as that gets bigger pretty soon, at some point, this thing starts to get large very quickly. And this is why we call this exponential growth. It can get big really quick. So this is when K is greater than 0, positive K, exponential growth. What does it look like for exponential decay? Well, it looks almost the same. It's almost like a mirror image, where basically this may not be a perfect graph. So this is what happens when K is less than 0, right? So for the decay, as x gets bigger, your function gets smaller. So it's decaying, it's getting smaller. But for the growth curve, as x gets bigger, your function is getting larger. All right. Now let me talk about one more little theoretical thing that's very important, and then we'll jump and do some examples. So hopefully a lot of this is review. You're following what I'm saying. Now it's interesting, everything I've talked about so far is stuff that theoretically you should have covered in your algebra class. I understand you may have forgotten it. Maybe even you never quite understood it in algebra. That happens sometimes. But this is really nothing new. And we really haven't done any calculus yet. Now we're going to add the calculus piece to these exponential functions. And you'll see what we're going to do, because in the problems we're going to work, in most of them, there will be a calculus piece involved. So let's think back. You just recently learned how to take the derivative of exponential functions. As a matter of fact, I'm just going to say this right now. Oftentimes in problems, they will ask about, they will say, what is the rate of change of something? You're going to see that phrase a lot in these problems we're going to do in a few minutes. When you see the word rate of change, basically they're saying find the derivative. So that's a big helpful clue in working these problems. A lot of times they'll say, what's the rate of change of this? And when you see this word rate of change in your head, you should think, aha, they're asking for the derivative. So let's take a minute and review. You just learned this. So if we take our basic exponential function and we want to now take the derivative. So a lot of times we can write the derivative, right? Now, what's the derivative? How do you take the derivative of an exponential function? Well, first of all, this f naught is just a constant that tags along. So remember, for an exponential function, you copy the exponential function and then you multiply by the derivative of the exponent. Now, t is my variable, so derivative of kt is just going to be k. Now, what I'm going to do, just so it's very clear, I'm going to sort of rearrange things. I'm going to bring the k way out front. And I'm going to put like a little multiply sign here. And then I'll write my f naught e to the kt. So here's a little equation for the derivative of my exponential function. But what's interesting is, look at this little piece here. And if I look up here, these are actually the same. And up here, I wrote this here because that's what I'm calling my original function. So just for fun, instead of writing this, I'm going to replace this with just f of t. Now this becomes important, and we actually use this a lot, because what they're going to do is, on some problems, and I'll do a couple examples in a minute, they're going to give you the derivative and the function and this k. Well, let me do this. Let me just do a couple of examples. Instead of me trying to describe it, this is one thing where if you just see an example, I think it'll be clearer. So for instance, maybe they give you a problem and they say, here's some kind of population growth problem. And what they do is they actually give you the derivative of this population function. And they say, for this problem, the derivative of the population is 4. This is exactly how they give it to you. The derivative is 4 times the original function. They will give you this, and they will say, based upon this, find the original exponential function, or in this case, they want you to come up with an equation for P of t. So let me try and describe what's going on here. This little thing right here, this only happens, this little setup here only happens when your initial function is an exponential function. That's the only kind of equation or function you can see this happen. So what that means is, as soon as they give me this, because look at this matches up with this, right? I've got the derivative, I've got a constant or a number here, and I've got the function. So these things perfectly line up. And you know what that says? That says this original function is an exponential function. And the whole key is, if I can summarize it, and if you understand this part, then you'll got what you need, even though you may understand what I'm saying. When you're given this kind of a function, the most important thing to know is that that number there is going to be the k. And I'm going to write my standard sort of exponential function. But when I have kt up here, because of this 4, I know it's actually 4t. In fact, the whole reason they give you this is sort of like to tell you what the k is, because you need to know the k if you want to write the exponential function. I mean, just for fun, they could give you another one, and they say, based upon this, figure out the original exponential function f of t. Well, exponential functions always look the same. They always fit this pattern. And the key is, I just need to figure out what k is. But once again, k is whatever this number is. So there, based upon this, I was able to come up with the initial exponential function. And they're going to ask you to do that a lot in these problems. So I guess you may or may not have followed everything I did, but the key is when you have something that looks like this number is the k. And they'll even change it up, because you know, sometimes they will have, instead of p of t, sometimes they'll write the derivative like this, right? You can also write a derivative like this, and they'll say, here is the derivative and the function, and they'll say, what's the original exponential function? Well, once again, that number in front of your function is k. So you simply say, in this case, it's 10t. All right, so they're going to give you a couple homework problems where they give you either something that looks like this or something like this, and they simply want you to write. And actually, in the homework, instead of this P naught or this F naught, sometimes I like to just write a capital C for everything. So I don't know if in the homework they want you to write the C, you can find out. All right, so now we're actually ready to do some example problems. So that was sort of a lot of it was review, although this part was sort of new because it involves calculus, because now we're talking about derivative. Oh, and I'm just warning you now, I won't talk about it now because you're probably tired of me talking theory. I'm warning you later on when we start working problems, I'm going to come back to this page and I'm going to say, Okay, with the question we're asking, we're going to use this little sort of formula equation here. I'm not going to say any more about it, but I'm going to save this page because pretty soon I'm going to pull it out and say, okay, here's where we want to use that. All right, so what I've done, I've tried to copy a few homework problems sort of out of the book, and it's broken up into exponential growth problems and then exponential decay. The math is pretty much the same. It's just some problems, something's growing, and other problems, something's decaying or dropping. So I think this first one, I'm going to do number 8 here. I think this is an exponential growth problem. So let's read it. Looks like there are 3 parts to it. I've got a few notes here, so hopefully we can ignore these for a minute. Pizza's Inc. is selling franchises or pizza shops throughout the country. The marketing manager estimates that the number of franchises N, so N is like the number of, let's say, pizza shops, would increase at the rate of 10% per year. Now they give this information, but then they're nice to you because they say that is, and then they give you a little equation here. dN dt equals 0.1 N. So think of N, the number of pizza shops, as like your function. What is this here? This is what I talked about. Here's the derivative of N. Here's a number times N. So just what I mentioned, this is the kind of equation they give you. So this describes how the number of pizza shops are growing. Let's look at the first question. Find the function that satisfies this equation. Assume that the number of franchises at t equals 0 is 50. So they're saying 2 things. They're asking for the function. So right here I wrote, they're asking us to figure out n of t equals what? And it's going to be an exponential function, because when they describe it like this, remember I said a few minutes ago, this kind of little equation only works if the original function is an exponential function. So by giving us this, they're telling us our functions are going to be an exponential function. As a matter of fact, let me just write it out here. So n is the number of pizza shops. Since it's an exponential function, all exponential functions look the same way. Your function equals n naught e to the kt. Very simple function. It's always the same way. Now, normally, to get the actual function in the way they want it, this n naught is a constant. It's a number. So a lot of times we like to plug in a number for this if we can figure it out. And k is also a constant. It's our growth rate, but it's a number. And we like to also figure out the growth rate. So if we can figure out these 2 things, then we will say we figured out the actual function. So once again, this is the number of pizza shops. And I think the time is in years. So we're looking at how many pizza shops are we going to have based upon how many years have passed. So this is the function, but then what did I just say? I talked about this little thing when you have, here's an example, an equation like this, where you have the derivative equals a number times the function. What did I say? The number in front of this function is k. Well, look what they gave us here. That's what they gave us here. So what is that saying? This number here, that's k. They've given us the k. And that's why they give you this little equation here, because they want a way to tell you what k is. So k is 0.10. So I can say can start plugging things in. E to the 0.10t. And now I would like to figure out my N naught, right? N naught is the initial condition. In this case, it would be the number of pizza shops at time 0, like when they start keeping track. So let's see if they give us that information. Look at part A. Find the function that satisfies this equation. Assume that the number of franchises at t equals 0 is 50. Remember, look at N naught. I said N naught is how many pizza shops you have when you start the clock. Well, the time is 0. We have 50 shops. Therefore, N naught must be 50. So I put in 50 for N naught. So then this is the answer for part A. Once again, let me just review this because we're going to do it over again. As soon as they gave us this kind of equation where the derivative of the function equals a number times the function. As soon as you see that, it's like ding, 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 alarm bells. You know that this original function is going to be a natural exponential function. So as soon as I see this, first thing I can do is go say, I know it's going to look like this. And then since they asked me to find this original function, I know that, hey, if I want the complete function, I've got to figure out a number for k and a number for N naught. Now, when they give you this equation, they're basically giving me the k. The k is always a number in front of the function. And then they gave me the initial condition, right? They said when the time is 0, there are 50 shops. So N naught's 50. Now, let's see what they ask next. How many franchises will there be in 20 years? All right, that's pretty straightforward because now what I have here is an equation that describes a number of pizza shops based upon what year it is. So they're saying it wants to look at when 20 years have passed, and it wants to know how many pizza shops we're going to have. So what do? You plug in 20 for t into this equation. So I could say N of 20 equals 50 e to the 0.10 times 20. So if I grab my calculator and do this calculation, this will tell me the number of pizza shops there are during year 20. So once again, hopefully it's not too hard for you to do this kind of calculation. 0.1 times 20 should be 2. I'll just do it here to show you. So 2 is the exponent of my e, so it's e to the 2. For my calculator, once again, I can go access my e to the x key. So this number here is e to the 2. I need to multiply it by 50. And I get 369.4. So now with story problems, a lot of times they'll tell you how many digits, but since we're talking about pizza shops, you would probably give the answer as 369. You round down in this case. So it's interesting, they started with 50 pizza shops. After 20 years, if their equation's correct, they've got 369. So they've grown a lot. So that's the answer for part B. So this is actually obviously an exponential growth problem. Of course, we should have known that because look at our number in front of the t, our k. It's a positive number. Even though it's a decimal, it's a small number, but because it's positive, it's still going to grow. Part C. All right, now here we go. Estimate the rate of change in the number of franchises in 20 years. So let's talk about this. So they're saying estimate the rate of change. You notice right here, I underlined the rate of change and I rewrote derivative. All right, that's what I said a few minutes ago. Whenever you see the phrase rate of change, that's like a code word for derivative. They ask for a rate of change, they're really asking for the derivative. And what they're doing is, but the way this works is the number is changing all the time. It's not constant. So they have to tell you when to look at this rate of change. And they say, look at it during the 20th year. When you're at the 20-year mark, how is it changing? So basically they're saying, what is the derivative when the time is 20 years? So in a sense, for part C, here's what they're really asking for. They want to know what is a derivative when the time is 20. All right, now here's where I'm going to go back. I said I'm going to circle this box, or I'm going to outline it, and we're going to use it because it makes it easy to solve. Because here's an equation that says the derivative of a function equals k times the function. Let me rewrite this for our problem. So our problem, we're using n for the number of pizza shops. So basically we're saying n of t equals k times n of t. And what we're hoping to solve, and it's starting to film me. Let's see if this pen works better. What we want is to figure out the derivative when t is 20. So what I can do here is I can rewrite this as the derivative for year 20 equals k times the function of year 20. Well, I know what k is. K is this 0.10. We figured out k way at the beginning. So I can put in 0.10 for k. And look at this. This is saying, what is the number of pizza shops during year 20? You know what they had us do in the second part of the problem? They had us calculate the number of pizza shops during year 20, 369.4. So I can plug in 369.4, and this simple calculation will tell me the rate of change. Matter of fact, I can do this in my head. Should be 36.94. Now I didn't write the units. Up here I could have wrote the units. For this one, the number of pizza shops during year 20, there will be 369 shops. But the rate of change says the units are pizza shops per year. So this is saying during the 20th year, at that exact moment in time, the way the company is going, they are basically building almost 37 pizza shops every year. Of course, that may change, in the next month or the next year, there's even a bigger demand. So they even are making more pizza shops, or maybe things happen and they make fewer. But that's what this derivative is. That's why this is called a rate of change. How much is it changing? So that's a very typical kind of homework problem you're going to have. And let me do another problem with a a little bit of a twist, because they don't all just give you the same kinds of problems. Now, some of these I'm going to try and go through a little quicker, because basically we're doing some of the same kinds of things. Let's look at this one, number 15. This is sort of a little bit of a money problem. 2013, the US federal receipts, so the money they take in, this is the amount of money the government takes in, total 2.77 trillion. So that's 2013. And then 3 years later, 2016, they took in 3.27 trillion. So the amount went up. Assume that the growth of total federal receipts F can be modeled by an exponential function. So they're saying, okay, we're going to try and come up with an equation for what's going on here. And it's going to be an exponential function. And they're saying, use 2013, that's when the clock starts, that's our time 0. And then they ask 3 questions. So they give you 2 years for 2013. This is the amount of money they took in. Then 3 years later, they took in this amount of money. So based upon this information, they're saying assume it's exponential function. Start looking at 2013. Now the first question is, find the growth rate to 6 decimal places. So they're saying find K, and then write down the exponential function FFT. So really they're asking 2 questions, although it's really the same question. Let me just make a few notes and we'll start working this problem out. So first of all, they say for year 2013, the amount of money they took in was 2.77 trillion. And then for the year 2016, they took in 3 point, you know what, I think I keep all these pens on my desk. I think they're maybe dying on me. Just grab a holding pen. Sorry about that. And they're saying use an exponential function. So let's just write it. Exponential function says f of t equals the f naught e to the k t, right? That's how they always look. Now they really ask us to find 2 things. They ask us to find k, but then they ask us to find this whole function. So really, it's really the same thing. If they ask us for the whole function, I would have to find k and f naught. So they're saying go find k, but when they say find the function, I would have to find k anyway. So it's sort of, it's like they're repeating themselves. So with these kind of functions, like I said earlier, you always have to find 2 things. These are constants. I got to figure out the number for f naught and the number for k. Well, f naught's pretty easy. This is the initial value. And they said, start looking, consider 2013 as like year 0. That's when the time is 0. So therefore, what would f naught be? Well, f naught is the amount during year 0. So it's 2.77. So I have 2.77. Now, if I figure out my k, then I'll have the equation. Well, I don't know k right off. Here's what I'm going to do. Because they told me in the year 2016, this is the amount of money, I can use this information to figure out k. So first of all, for the year 2016, what would t be? Well, t would be 3, right? If 2013 is year 0, 2016 is 3 years later, so t is 3. Here's what I'm going to do. I'm going to plug in 3 in for t. I'm going to plug in this amount in for my function. And when I do that, you'll see that there's only one looky here. The only thing that's not defined is k. And you know what I can do? I can take this equation, actually solve it for k to figure out what the number for k is. Now we did this a little bit ago. I said we're going to be doing this a lot, where you've got the variable up in the exponent, you have to solve for it. Remember what you do, you get the exponent by itself. So you say e to the 3k equals 2.77. Whoops. You take this divided by this. 3.27 over 2.77. I'm going to leave this like this for now, because now to get at the k up here, I'm going to take the natural log of both sides, right? So you take the natural log, I'll just write it out. I could skip a step, but just for one more time, just make it very clear. The natural log of e to this ends up just being the exponent. Now here I am going to skip a step because I'm going to divide both sides by 3. So now I have natural log of all this stuff divided by 3. That should equal k. So I'm going to take 3.27 divided by 2.77 equals. Now I'm going to take the natural log of this whole thing and then divide it by 3. Now, for some crazy reason in this problem, they said they want to know k up to like 6 decimal places, which is sort of crazy. So it's going to be 1, 2, 3, 4, 5, 6. So there's k. So now I can plug in k back into here to have my actual equation for the amount of money. So it's 2.77 E, and I got this k here, 0.055314 times t. So there's my exponential function. So all of that was part A. So I found my k, and then I found the function. Now let's say estimate total federal receipts in 2020. So now they give me a specific year and said, okay, so how much money came in during 2020? Well, please don't plug in 2020 in for t, because what you have to do is you have to remember the clock started at 2013. T equals 0 at 2013. We're talking 2020. So what's t going to be? T is going to be 7. So now I'm going to plug in 7 for t into my function to answer the question they're asking. 0.055314 times 7. Now, actually, I left this number in here, so I can take it times 7. And now it's e to that, so I have to do the exponential part, then times 2.77. So in the year 2020, now here they may tell me what to round to. They don't say estimate total receipts. Maybe I'll leave 2 digits like all these. So I'll say 4.08. So that should be the answer for part B. And then part C, when will total receipts be 10 trillion? So this is like the problem I did earlier. Now they're saying, hey, tell me how long it's going to take or when the federal receipts would be 10 trillion. In other words, so far in this problem, we know that in year 0, it's 2.77. In the 3rd year, it's 3.27. In the 7th year, it's 4.08. But they're saying, what's the year for it to get to 10? Right, so far we've seen 2.77, 3.27, 4.08. They're saying, how long until it gets to 10? So that's where you take this equation and I put in 10 for f of t, and then I have to solve for t. So 10 equals 2.77 e to the 0.055,314 t. Let me write down this a few times, right? We're going to divide both sides by 2.77. We'll take the natural log of both sides. When you do all that, you end up with something like this. So I can take this natural log and divide it by 0.05534, and that should be t. So I'm just going to do this on my calculator, save a few steps. So 10 divided by 2.77. I'm going to take the natural log of it and divide that by 0.055314. I get 23.2. So basically, it's going to take a little over 23 years for the amount of money to get to 10 trillion. All right, so those are 2 examples of exponential growth. And actually, let me do one more quick one, a pretty straightforward money one, because I wanted to give you an example, because I told you that, if I can find it, I'll print it out. As I told you, I think this is it right here. So let me, in terms of money, let me say this again. Anytime you have a money problem and you see the words compounded continuously, right away, you can say, I don't know which one to use for money. We can say A of t is the amount of money equals A naught E to the RT, where R is like the interest rate, not in percent, but as a decimal. And we'll do an example in a minute. So R, see here, actually, I put an R there for interest rate. To be consistent, I should have called it K. But a lot of times I call it R because for a money problem, the growth factor for money is called an interest rate. And that's why sometimes they put an R instead of a K for interest rate. But be clear, if they say 3% interest rate for the problem, you do not plug a 3 in for K, you turn this into a decimal. Hopefully you remember how to turn percents into decimals. You always have to move it to the left. 3% as a decimal is 0.03. So you would stick in 0.03 for K. All right. This is why I want to do one money problem, because it's the same equations, but the words they use are different and it might be confusing. I'm going to look at 46 here. This is called a present value problem. Desmond wants to have $15,000 available in 5 years to pay for new siding. Interest is 4.3% compounded continuously. How much money should be invested? So a couple of things are going on. First of all, the basic problem is Desmond tells himself in 5 years he wants to do some new siding. He knows it's going to cost $15,000. So he said, how much do I need to put in the bank today so I can go to the bank in 5 years and it'll be $15,000 sitting there. So he's told, or he knows he can get 4.3% interest, and he's going to do it for 5 years. Now the key is, it said 4.3% compounded continuously. There are those keywords. Once they say that, then I know what my equation is going to look like. So let's write out the equation and see what we need to do. So I've already got it written here. This is the equation. We'll call this for money growing in the bank. However, well, let's first put in interest rate. Interest rate's 4.3%. However, that means K is going to be 0.043, right? You got to move the decimal 2 to the left. So I say A naught e to the 0.043 t. Now in this case, what's happening is he wants to take 5 years and he wants to have $15,000, and he's saying, how much do I need to put in the bank today? So really, we're really trying to solve the initial amount. The initial amount is how much money he puts in the bank today. And then in 5 years, he's going to pick up $15,000. So hopefully you see that I put in $15,000 for this. I don't know the initial amount. I know my interest rate and my K is this. I know he's going to do it for 5 years. If you look at this kind of problem, the only thing I don't know is A naught, so I can solve for A naught. Matter of fact, what I should probably do is take this number and go and calculate it. So I can grab my calculator. .043 times 5 equals. Then I need to take that as an exponent. So this is 1.23986. If I want to solve for A naught, I'm going to take 15,000 divided by this. And when you do that, I can do that quickly on my times 15,000. 12098. I think it says to the cent, or it doesn't really say. We'll go to the cent. So he has to put a little over $12,000 in the bank today, so that in 5 years he can come back and he can get $15,000. So it's interesting. This problem really didn't involve calculus at all. This is like an algebra problem, but these are the kinds of problems in the homework, so I guess they really want you to get this. So far, these have all been growth problems. Let's do a couple decay problems. And then hopefully you'll be able to figure out the homework on your own. So maybe 2 problems. All right, let's look at this one. Radioactive decay. They even call it decay. So this is some kind of element or chemical or something. Curium-245 has a decay rate of this much per year. The rate of change of amount N of curium-245 after 2 years is given by. Okay, now we're back to this. Hopefully this looks familiar. The amount of curium is N, but they give us equation for the derivative equals a number times the function. Hopefully right away you're starting to think about what this means. So we'll come back to it in a minute. Let's look at the first question. Let N naught represent the amount of curium present at t equals 0. Find an exponential function that models the situation. So part A, they're saying, once again, when they give you this kind of equation only applies if you have an exponential function. So we know we have an exponential function, and they're saying, first thing to do, go find the exponential function. And they say, just leave it as N naught. They're not going to give us a number yet. So just to refresh your memory, if I even have my notes, it's getting messy here, but way back when I first started talking, I showed you how you have this special kind of equation with a derivative, that is a way for them to tell you what K is. Right? So this right here goes back to this right here. And the number in front of your function is the K. So for this one, they're basically saying K is negative 0.0000815547. So let's go ahead and try and write out the function then. So N is going to be our function. So N of t equals, now they said just for now, call your initial value N naught. They're not giving us a number, so I'm going to leave it N naught. But then I'm going to put in this K, which is negative 0.0. I think there are 4 zeros. 2, 3, 4, 8, 1, 5, 4, 7 times t. So that's the answer to part A. And the whole key to that is because they give you this little equation here, they're giving you the K. Once you've got the K, you can just plug it in, and we've got the exponential function. B, suppose 60 milligrams of curium-245 is present at t equals 0. All right, hopefully once again, once they give you times 0, what are they doing? They're giving you the initial value. So they're saying at times 0, you've got 60. So 60 is my initial value. So they give you that piece of information, and then they say, how much will remain after 1,500 years? So the first thing they do is they give you your N naught, and then they ask you to work out a problem. Let's first plug in N naught. So N naught is going to be 60. So the first thing I can do is rewrite my equation to be 60 e to the negative 0.00081547 t. And now they're saying, go plug in 1,500 years for time and tell me how much is left. So I'm going to plug in 1500 here. I'm going to do this on my calculator. So 1500 times all this raised to an exponent times this. Let's just do it on my calculator instead of writing it. So I'm going to start with, I'll type in this big long constant. It's 0.12340811547, and it's negative. Now it's times t, and t is going to be 1500 years. So times 1500. So this is now my exponent. So for me, I can hit these buttons and have it calculate that as an exponent. So now this is going to be multiplied by 60. 53, let me ask for significant digits and stuff. It doesn't, so I'll just call it 53.1. So this is pretty slow. So this is like grams, I think. Yeah, grams. Or milligrams. It's interesting, it began, this value was 60. We went 1500 years and it dropped this much. It's pretty slow. It's decaying, but it's pretty slow. It's not decaying very fast. Part C, what is the rate of change? There, I've underlined it. Why is that? I said earlier, rate of change right away should tell you you're looking for the derivative. What is the rate of change of the amount of curium after 1500 years? So once again, rate of change is going to be the derivative. And they actually want to know what it is when the time is 1500 years. Now I go back to this very handy equation. I said I was going to refer back to it, where the derivative of a function equals the k constant times the initial function. Let's rewrite this equation for this situation. So we're looking at when the time is 1500. I could write k here, but I know k is this. Let me just go and write it out. That's k right there. 81547. Right. The equation is the derivative equals k times the original function. The original function, we're looking when the time is 1500. Oh, sorry. You probably noticed this. I should have called these n's. But you know what? That's what I'm trying to find. I need to know n at 1500 years. And what's nice is the part before, part B, we calculated in at 1500 years. It's 53.1. So I can plug that in here. And basically this number times 53.1 will be the rate of change at time 1500 years. So once again, got this big long point 0.00081547 negative times 53.1. Pretty small number, negative 0.004. I'll just call it 433. So for this one, it is milligrams per year. So it's saying the rate of change is negative. So it's dropping, it's decreasing at a very small rate. All right, so once again, this little equation makes it pretty handy to do that calculation. But there is a fourth part. After how many years will half the original 60 milligram Ethereum remain? All right. So they're saying, now they're asking for a time. We know there was originally 60 milligrams. They're saying, how long will it take until half of this is gone? Which would mean when there's 30 left. So we've sort of done this before. So once again, here's our equation. 60 is the initial amount. I'm going to plug in 30 for my amount and then calculate t. So it's going to be 30 equals 60, 0, 0, 0, 0, 8, 1, 5, 4, 7, t. So if I want to solve for t, first thing is I divide both sides by 60. And here's what's interesting. Turns out this is sort of a special problem because in the world of science especially, it's pretty common that they do these half-life problems. Half-life means you start out with a certain amount and they're looking for the amount of time that half of this goes away. So these apply to problems where it's decaying, where the amount is getting less and less. And the half-life says, okay, how long until your original amount drops by half? So in this case, of course, I'll take the natural log of both sides. I'm going to divide by this negative number here, and that should give me the time. So I'm going to take natural log of 1/2, which is 0.5 natural log divided by 0.000081547 equals. And that should be the time. It's like a long time. Basically, if we round 8,500 years. So now I haven't checked all my numbers, so I just hope I did all my calculations correct, but I may have made a mistake, but the method obviously is correct. We always might make mistakes with the calculations, but all right, one last decay problem. And I believe this is the, let me find it. I just had it here. Got too many papers scattered out on my desk. All right, here it is, number 31. Last one. Iodine 125 is often used to treat cancer and has a half-life of 60.1 days. In one sample, the amount of iodine 125 decreased by 25% while in storage. How long was the sample in storage? Wow. So let's see what's going on. So this is the problem where they talk about this half-life thing. So let me just write down the information. So iodine 125 is used to treat cancer and has a half-life of 60.1 days. So and they say in one sample, the amount of iodine decreased 25% while in storage. How long was it in storage? So they don't really give me a whole lot of information, but here is why half-life becomes important. Let me just write out our basic exponential equation. I'm going to, from the start, I'm going to divide both sides by n naught. I'm going to get the exponential by itself. And then we're going to talk about what we have. So this n naught is the original amount, or what I call the initial amount. And then, now in this case, because we're talking about a half-life, this is the amount left. Or the amount, yeah, let's call it the amount left. So you take the amount, so half-life is the amount of time it takes for half of your stuff to disappear. So the amount left, or the amount you start with, hopefully you can see, has to be 1/2. That's what half-life means. Half of it goes away. So for instance, say we started with 10, and the half-life means the amounts drop down to 5. So if I put a 5 in here and a 10 in here, 5/10 is 1/2. It doesn't really even matter the amount. Say, what if I started with an amount 50, and then after the half-life, of course, that's when half of it disappears. You're at 25. So then if I do this calculation, 25/50 is 1/2. So I don't even need to know these amounts. I just know this ratio is always 1/2. So here's this equation, and it tells me the half-life time is 60.1 days. So I can put in for T 60.1 days. Because you know what I can do now? I can figure out what K is. So it's interesting, by simply telling me the half-life time, they're in a sense, they're giving me a way to calculate my growth constant. And that's why a lot of times they will give you the half-life times, because it's a roundabout way for you to calculate your K. So let's do that. So this is going to be natural log of 1/2 divided by 60.1 days equals K, right? We've done this before. So if I did this calculation, (1/2) natural log divided by 60.1. So K is -0.01153. So now I can write my equation for this iodine, or whatever it is, as, I still don't know the initial amount, but now I do know my K, 0.11. Now, so the first part of the problem, giving us the time of the half-life, gives us a way to find K. Now let's look at the rest of the problem, what they're really asking. So now they're saying in one sample, the amount of iodine decreased by 25% while in storage. How long was the sample in storage? So once again, they're not actually telling us how much we started with, but they are saying it decreased by 25%. So just for fun, here's one way to think about it. Since they don't give me the amount, I tell them how much decreased, let me just assume, I'm going to assume I start with 100. Now, if it decreased by 25%, then at that point, the amount's going to be 75, right? Going from 100 to 75 is decreasing by 25%. So let's plug these numbers in here. So I'll put a 75 here and 100 here. Now, if I can solve for this time, this will be the time it took for it to decrease by 25%. Divide by 100. Of course, take the natural log of both sides. It was negative 0.01153 t. And now, with my calculator, I can take 75 divided by 100, take the natural log of that, divided by 0.01153, negative 24.95. Now this was days, so it took almost 25 days for this amount to drop by 25%. That's an example of why you have to understand half-life, because it becomes important in some of these problems. All right, so that's exponential growth and decay. Hopefully those examples will help. Not all your homework problems are going to be exactly like these examples, but hopefully you understand the principles and you can figure things out.